Alright everyone, welcome back here. So we're going to start off with another pretty straightforward problem here. We're going to look at the area of an equilateral triangle with side length 4. Okay. So I'd like you to try this problem out on your own first before we actually do it together here. But I'll go ahead and sketch our triangle like this. I'll call this triangle PQR. So the goal here is finding the area of PQR. Alright, so the first thing to note is that, well, we know that an equilateral triangle is also equiangular, which means that all the angles are 60 degrees. So I'm going to go ahead and mention this here. So this is 60, and this is 60 down here. So in order to calculate the area of this triangle, we need the height of the triangle, which means I'm going to need to draw an altitude of some sort to the base. So let's do that here. I'll draw up an altitude like this here. I'll call this point here S. Now, one thing to note here is that you can very easily show that using whatever method you want here, in this case, angle, angle, side, two 60s, two right angles, and this side PS that's in common to both, we can show that these two triangles are congruent, which means that QS and SR are the same, so that 4 is split into 2 halves, so it's 2 and 2 here. Now, we don't know what PS is, but I think we can figure that out here by using the Pythagorean theorem. We kind of have this sort of thing here. So, therefore, we can say here that 2 squared plus PS squared equals PR squared. Or I guess I should have put in 4 here. We can do that now. 2 squared plus PS squared equals 4 squared, right? So therefore PS squared is going to be equals 16 minus 4. So PS squared is 12. 12, sorry. So PS is therefore the square root of 12, which, again, we can pull out a square root of 4 here, and we're left with 2 radical 3 like so. Okay? So now, as a result here, ladies and gentlemen, we can kind of do the same idea. We can kind of set this up here, and therefore say that the area is this going to be 1/2 times the base, which is QR, times the height, which is PS. So it's just 1/2 times 4 times 2 radical 3 here. One copy of the 2, a 2 drops out with the 1/2 here, leaving a 1, and we're left with 4 radical 3 as the area of the triangle here. Okay, very nice. So note that in this situation here, what we had is an equilateral triangle that's been divided exactly in half. It's almost as if it were a sandwich of some sort, and you're slicing it down the middle. Notice that we can actually fill in the other pieces up here. This segment PS is not only just bisecting the base, it's also bisecting the angle on top here. It shouldn't be too hard to show. Therefore, we can actually find out here that these two angles on top are 30. So this is 30 and this is 30 here. And now we can see that we have ourselves another triangle that's related to the 45, 45, 91. One that has specific properties like this here. We note that we have this sort of thing going on here, where you see that it seems like the short side and the long side are a 1-to-2 ratio here, right? The hypotenuse is double the short side, and you have this radical 3 business here, okay? So just to be sure, make sure that we're on the right page here, we can go ahead and try this again, this time with a slightly different situation here, right? Again, it's kind of like what we did with the 45, 45, 90 triangle here, and we're going to do this in general. So yet again, right, we can do the same thing here. I'll call each of the sides here, I'm going to call them 2x. Because if they are indeed split in half, I kind of want that 2x to be there. I don't want to have any fractions if I don't have to. This is 2x on the bottom. So yet again, just like before, we can drop an altitude, in this case from the upper vertex A down to BC. We call this here D, and yet again, by the same token, we can kind of fill in everything here. So this is x and this is x here, and then AD, we can just fill that in. So therefore, we can say here that AD squared plus DC squared equals AC squared. So we just fill in the pieces that we know. You have AD squared plus x squared equals 2x all squared here, right? And that should work out very nicely. So you get AD squared plus x squared. The 2x times 2x is just 4x squared here. So you get AD squared equals 3x squared because we subtract x squared from both sides. And therefore AD is just, we can take the square root of the 3x squared. And we note again, there's a perfect square here. There's an x squared in that, right? So I can yank that out, and we're left with x squared times radical 3, square root of that at least, and you have x radical 3 here. So this here, ladies and gentlemen, this what I have here, this triangle is our archetypical 30, 60, 90 triangle. We name it by its angles just like we would with the isosceles right triangle here. So the 45, 45, 90 triangle, notice that we actually created that by cutting a square in half diagonally. The same idea occurs here. We can cut an equilateral triangle down the middle like this here. So notice that in this situation here, this is your 30, 60, 90 triangle. Right? So the key here is that this short side is always 1/2 the hypotenuse. Or you can kind of pour it the other way around. You can say the hypotenuse is double the short leg. And then the longer leg equals the square root of 3 times the short leg. And that's where this whole x, 2x, x radical 3 comes from. So it's almost like a 1, 2, 3 here, except that the 3 at the end we take the square root of that. So you have 1 radical 3 and 2. Those are the ratios of the sides here. And that's always going to hold in the 30, 60, 90 triangle. And that's going to be important to us as we go. So keep that in mind here, ladies and gentlemen. Now, with that in mind, we can actually go back to our, a triangle like this here. We started off by trying to find the area of this equilateral triangle. So we can kind of do it again. Notice that we have, this general equilateral triangle, and it'd be a shame for us to just drop it right now, right? So we can kind of do the same thing here. And this time I'm just going to scale everything down by a factor of 2 because I want the side length here, right? So we can kind of do the same thing here and then just divide all the sides by 2 because I want, in this case, something with the sides only. So we have this sort of thing here. Here's our side, here's our side, here's our side. And again, we drop an altitude like this, and this is s radical 3, right? So now the area of the triangle ABC here, again, is just 1/2 the base, which is BC, times the height, which is AD. I guess D we have here, right? So it's going to be 1/2 times BC, which is S, times AD, which is s radical 3. Now, we have to be kind of careful. I actually did make a mistake here. Notice that this s radical 3 is what it was over here. We actually have to divide this by 2 because we have DC, the short leg is not s anymore. It's s over 2, right? This is s over 2 here. This is s over 2. And this entire thing here is now s, so I apologize about that. So this is going to be s radical 3 divided by 2 here. Okay, and now we can put this all together. So notice that in the numerator we have, there's nothing to cancel. So the numerator, we just gather all the terms. We have 1s, s, and s radical, 1s, s, and radical 3. So that's 2 copies of s squared. We have a radical 3, and the denominator is 2 times 2, which is 4. So notice that this here, this is important here. I want you to focus on this. This is the area of an equilateral triangle with side s. Now, again, if you're a big fan of formulas, you can memorize this formula, and that's perfectly okay. You can use that and see what you would like to use with this here. But note that as long as you understand where it comes from by just simply dividing an equilateral triangle in half, you don't need to memorize the formula here because you can just very easily rederive this yourself. You can still use the classic 1/2 base times height. Here, we're just finding a way to calculate the area of this triangle without having to resort to figuring out what the height of the triangle is, because that might be a bit of a hassle. Nevertheless, this all still works here, and this is just another way, bit of a shortcut here, so to speak, to find the area of an equilateral triangle.